Hi, can everybody hear me? Is this on? Good. Okay, great. Thank you so much, Noah, and thank you, Kristen and Edward, for having me here at Virginia Tech these past 2 days. I've greatly enjoyed meeting a number of you and learning about your work, and it's really inspiring to see the way that Virginia Tech is engaging with materiality. As Noah mentioned, I'm an associate at Shigeru Ban Architects. So I was drawn to Shigeru's work in part because of the humanitarian end, but also the environmentally conscious work that he pursues, which in large part engages structural and material innovations. So this afternoon, we'll be specifically talking about working in interdisciplinary collaboration to facilitate the design and construction of complex timber structures. We'll start with a brief overview of Shigeru's work, followed by a primer on timber and mass timber, and then end with a look at some timber case studies. So to begin, Shigeru Ban Architects is a global practice. We have offices in Tokyo, Paris, and New York, and over 165 works worldwide, including paper, timber, and other materials. In 1985, Shigeru's first professional project was an exhibition of, sorry, am I losing? I could also just shout if that helps.
Would you be fine holding?
Yeah. Okay.
Sorry about this.
Okay. Is that okay? Okay. In 1985, Shigeru got his first professional commission, and this was right out of undergrad. He was commissioned to design an exhibition of Emilio Ambaz's work. And in the process, he discovered paper tubes at the center of fax paper rolls and rolls of fabric. And he decided that this was too useful of a material to throw away. He noted that the paper tubes were strong, lightweight, inexpensive, recyclable, and available worldwide. So later that year, he was commissioned to design an exhibition of the work of Alvar Aalto. And he had initially hoped to use wood as a nod to Aalto's Vipuri library ceiling. But given the cost and waste associated with using this for a temporary exhibition, he opted for paper tubes instead. A decade later, in 1995, Shigeru designed a weekend home for himself, which is called the Paper House. It's the first building in the world that was permitted to use paper tubes as primary structure. But Shigeru often jokes that he hasn't seen it since because he just doesn't have the time. This paper tube work is probably a bit more familiar as Shigeru is constantly engaging with humanitarian work. So he's designed disaster relief shelters around the world, and this typology is called the paper log house. So in the upper left, you can see the original paper log house from 1995 in Kobe, and the other images on screen are of more recent iterations, which were adapted to the local climate, culture, and construction practices. This timeline displays the progression of Shigeru's work from inventing with paper tubes at the outside of his career to the more complex mass timber structures of today. But there isn't a distinct change from one era materially to another. His timber innovation dates back to the 1990s and continues in parallel with the paper work that we continue to do today. So regardless of the material, this breadth of work demonstrates that structure and materiality are integral to the design process rather than merely being the means of executing a predetermined concept. Shigeru's work is chronicled in Paper and Architecture, which was published in 2009, and more recently, Timber and Architecture. And one thing I want to stress in this talk, whether it's a building, an exhibition, or even a book, architecture is not a solitary endeavor. This is probably 50% of the team that had a hand in creating Timber and Architecture. It took a global and interdisciplinary effort across all of our offices, current and former staff, engineers, fabricators, digital facilitators, as well as the production team at our publisher, Rizzoli. So we'll take a quick look at Timber and Architecture. The book begins with 3 guest essays to contextualize the importance of the subject of timber. There's a foreword by the environmentalist Paul Hawken, and then Shigeru's own essay, Why I Love Wooden Architecture. Next, we have Herman Bloomer's recounting of his career trajectory from carpenter to timber engineer. The body of the book presents 45 works from conception through to the completion of construction, as Noah mentioned, which demonstrates the merits and challenges of building with wood. So this isn't just the glossy finished image of what we wanted the building to be, it's all the struggles that it took to get there and how constraints informed the design process. The projects range in scale, budget, and program from prefabricated wooden houses to parametrically modeled glulam grid shells, which shows the true spectrum of what you can do in wood. The book concludes with an index of all of the work that Shigeru Ban has done in wood, both unbuilt, built, and also our current work in timber. SBA has more than 75 built works in timber around the world. So one important point in organizing this book was not to go chronologically from the 80s to the present, but instead to arrange the projects thematically according to structural typology. This helps show the influence of budget, code, regional tree species, access to skilled labor, and even the local fabrication capabilities. But before we dive into projects themselves, we have to stop and ask, why wood? This is something that my colleagues and I are asked nearly every time we present. Why wood? Wood is a beautiful, versatile material with diverse structural possibilities. It's sustainable and renewable and can often be locally sourced. With off-site fabrication, timber construction sites are typically cleaner and safer, and construction schedules are typically quite short. You may be familiar with the term biophilia. People naturally feel better and healthier in buildings with visible natural materials, and psychological studies have shown that this also increases productivity. Now more than ever, it's imperative that everyone from architects and builders to clients and even the general public gain an understanding of how construction impacts the environment. Issues of waste, permanence, and material selection are crucial considerations in a holistically sustainable approach to design and construction. So you've probably all heard the statistics. Buildings account for nearly 40% of the world's carbon emissions, with 11% due to construction alone. And in terms of embodied carbon, wood far outperforms alternative structural materials like steel and concrete. But it's reasonable to understand the concerns about wood. First, what about deforestation? Contrary to popular misconceptions, the use of sustainably sourced wood from small diameter trees actually helps promote the health of forests. So this helps to prevent forest fires, and it makes them more resilient. Next, isn't wood expensive? So a couple of us were discussing over lunch, people often think only about the unit cost of a material, but reductions in on-site labor time, construction duration, yield considerable cost savings across the life of a project. Next, is it safe? Won't it burn? Fortunately, sufficiently thick wood burns at a slow and predictable rate, and like any structural material, factors of safety are required. At the bottom left, you can see the results of fire testing. So oversizing the structure allows for a sacrificial layer that can char without compromising the core of the structural member. This charring acts as a protective layer, slowing the rate of combustion and insulating the core of wood. Finally, will it last? Coincidentally, as a Japanese firm, the oldest timber structure in the world is in Japan. This is the Horyuji Temple, which is more than 1,300 years old. It still stands today in part due to its strong and durable materials, robust structure, precise detailing and construction, but also because it's of great cultural significance. And as Shigeru often notes, if a building is loved, it becomes permanence, and that concept transcends materiality. Buildings that are meaningful to their communities are cared for, and that's actually the most environmentally responsible approach that we can take. It's not to continuously build and build and build, it's to build buildings that are invested in by the community and that people truly take a sense of stewardship with, to keep them for generations to come. Wood is also not always the answer. Each of the bullet points listed here could be a deterrent for building in wood, or it could be the starting point for developing an innovative response in the face of constraint. For example, what do you do if the building code doesn't allow mass timber, but you want that warm biophilic expression of wood? This is an older project, it's about 25 years old. Ironically, Shigeru's found that in Japan, there are some of the most restrictive building codes, so he can't build in mass timber in most urban conditions in his own home country. The misconception in this case is that mass timber buildings are not safe, but in actuality, the building code just hasn't caught up to the realities demonstrated by fire testing. So Shigeru grappled with this in the year 2000 when he was commissioned to design a new office and showroom for a dental company. Since a timber structure wasn't allowed, he opted to work with steel for its strength and ability to span long distances. Steel typically requires a fireproofing layer known as encapsulation, and this could be drywall, for example. And so that prevents structural damage in case of a fire. This is typically clad with a finish-grade material to improve the appearance. But subverting the logic, Shigeru demonstrated to the code officials that wood could actually be used to fireproof steel. Fire resistance tests demonstrated that 50 millimeters of wood, which is about 2 inches, it adequately addressed the building's 1-hour fire rating requirement. So therefore, he used 2 layers of particle board with a finished layer of plywood to encapsulate the steel. Despite not being a timber structure per se, the building retains the warm aesthetic of wood. More recently, he had a similar set of conditions, again in Japan. This is Tamatic Nagoya. The aerospace and automotive engineering company was particularly interested in biophilia, wanted a mass timber building, but was not allowed to have a mass timber building in an urban context here. So to satisfy the client's aesthetic desires, environmental desires, this 8-story building uses CLT, which is cross-laminated timber, as permanent formwork. So you can see at the diagram on the right, first the rebar is set up, then a box is created with cross-laminated timber, it's filled with concrete, and then instead of removing that formwork, it's left in place as the interior finish for the building. The use of permanent formwork has many benefits, most notably the biophilic benefits of wood, and a shortened construction schedule from not having to remove that formwork, but also a reduced carbon footprint by not having this sacrificial material that would literally have gone in the trash. Additionally, no further materials were needed for a finish layer. Returning to our list, the availability of materials and skilled labor could also be a deterrent for using timber. Simply selecting wood doesn't make it a sustainable choice. So for example, if you're considering spruce from Switzerland and your project's in California, choosing that wood does not make it sustainable. And sometimes the topic of local materials is less about what wood species are regionally available and more a matter of which building materials are locally available. So in one of SBA's early projects, Shigeru was commissioned to design a house on a remote wooded hillside. It was very difficult to access with construction equipment. And so the only material that Shigeru could get to the site was plywood. He decided to design prefabricated plywood furniture units. So those were closets, bookshelves, other casework. And that casework was then used as the structure for the building. So instead of having freestanding columns, he had a bookshelf that acted as a column. This was designed and fabricated off-site and then brought to the site ready to assemble in a matter of a week. This reduced the construction time, material waste, and need for on-site skilled labor, which yielded both cost savings and a higher quality building. So here you can see the prefabricated furniture units. There are 33 in all. Each weighs approximately 175 pounds and could be easily maneuvered into place by just 2 people. This is kind of a hallmark of Shigeru's design. I believe there are now 7 furniture houses that he devised a structural system and then continued to iterate on it, improve on it over time. So as we continue through this list, hopefully you come to understand that these potential pitfalls are also opportunities for innovation. It's the chance to think creatively and materially and to engage structural engineers, fabricators, builders, material testing facilities, and code officials, among others. So that's all the common sales pitch for why wood. That could apply to any architect from any firm who wants to use the material. But why specifically does Shigeru Ban have an interest in wood? Shigeru actually wanted to be a carpenter when he was young, and so he's always had this specific, tangible relationship to the material. And he acknowledges the limitations of wood. That's precisely what intrigues him. So similar to that list of why not wood, he wants to operate in that space of trying to find the problems and exploit them. So whereas steel and concrete can easily take on any number of shapes, you really need to understand the properties of wood to optimize its structural form. And by leaving timber unencapsulated, this allows the material to serve as both structure and finish, which is a materially authentic approach. expressing the beauty and efficiency of rational structural forms. To do this, we need to collaborate. So from the outset, SBA engages a core team of engineers and fabricators and builders to see these real-world constraints as opportunities. Shigeru has great respect for his collaborators, so his introductory essay in the book is devoted to his close working relationship with these three structural engineers, Gengo Matsui, Frei Otto, and Hermann Blumer. With Gengo Matsui, Shigeru brought his early paper tube concepts to fruition, advancing beyond simple upright columns to complex building forms. This was further advanced with Frei Otto. Here, Shigeru fully delved into form finding, and you can see the influence of Otto's Mannheim multi-hall on Shigeru's Japan paper tube pavilion. And lastly, we have Hermann Blumer, who also wrote an essay for the book. Hermann also began his career as a carpenter before switching over to structural engineering, and he pursued a PhD in structural engineering in 1969. At the time, he was the only person in his class who wanted to pursue a thesis on timber, and his colleagues and professors actually thought that the subject wasn't complex enough to warrant doctoral study. But Hermann persisted, and he became a pioneer of digital fabrication. He later designed the first fully automated CNC machine. You can see the breadth of his understanding of structure, materiality, and craft here in the Nine Bridges Golf Clubhouse. Okay, does everyone know what mass timber is? Yes, okay. We'll do a very, very brief overview here. So in contrast to dimensional lumber, which is composed of a single piece of wood cut from a solid log, engineered wood products are manufactured wood products. They're a composite that could be made from wood veneers, strands, particles, and either an adhesive, nail, dowel, etc. So graduating in size, mass timber is also an engineered wood product with lumber from small diameter trees bound together by the same adhesives, nails, or dowels. And this has two primary advantages. First, it dispels any myths about, are you cutting down the rainforest? No, we're using small diameter trees. So we don't need old growth trees. And second, because it's a composite, mass timber is actually a standardized product with predictable strength characteristics. So by using multiple pieces of wood in a single member, you're kind of homogenizing the structural profile. Common examples of mass timber include glulam, cross-laminated timber or CLT, LVLs, DLT, which is dowel laminated, NLT, which is nail laminated. Mass plywood panel is a newer one, that's MPP, and dowel laminated timber, which is DLT. So on the left here, you can see an example of heavy timber, so that's solid wood. And on the right, you can see an example of mass timber, so that you might be able to see the tiny joint lines in those individual beam members. So before we actually dive into the projects, we'll do a quick recap of 10 key considerations to keep in mind when you approach a mass timber project. These points are applicable regardless of the complexity. So if it's a simple house or a complex grid shell, these considerations remain the same. So first, we have to ask, why wood? Is this the right material for the project? Oftentimes, a hybrid solution is the appropriate response. Next, we review the building code to understand what you can do in a given jurisdiction and establish the building type and the fire rating. From here, we can establish the structural grid, and that would involve considering spans and member sizing in relation to vibration and deflection. Once the grid is established, then you can think about the MEP strategy. Are the building systems going to pass through the structure or bypass it on the underside or above? Will it be exposed, etc.? And lastly, how do we optimize the volume of wood to both minimize material waste and site erection time? And then we can think ahead to constructability. Design for economy might not sound like the most fun topic. It's literally the most fun I have all year. It's like trying to solve a puzzle with the smartest engineers you can imagine. So ideally, you want to meet with these potential engineers, mass timber suppliers, et cetera, at the outset of the project so that your design is informed by these real world factors. So as you're considering species of wood, you have to think, is it native? If you're in the Pacific Northwest, you're most likely thinking of a spruce pine fir material. Or if you're in the South, it's more likely a southern yellow pine. You also want to consider the manufacturers and fabricators' geographic proximity to your site. So if you have a local, like let's say you're building in Arkansas, you want to use southern yellow pine, but the best fabricator you know is in the Pacific Northwest. It makes no sense to source your materials locally, ship them up to Oregon, and then ship them right back down again. You might as well use materials in Oregon at that point. So today, you simply can't fabricate the same projects in the US as Switzerland, for example. So you also want to tailor your design approach to what can be created in the country that you're in or in the region that you're in, because that's also a far more sustainable approach to design. So rather than designing something to be fabricated abroad and shipped over, try to work with your regional and local fabricators. And lastly, you begin to outline the site erection strategy. And this is something that we're often doing in schematic design. And that incorporates everything from how many truckloads of material it takes to get you to the site to how you stage the site to plan for construction. We'll spend the remainder of our time looking at three primary structural typologies. First is post and beam. Next, we'll have space frames. And lastly, grid shells. So I know many of you have spent time in Switzerland and seen this project. I'm very jealous of Edward's class and wish I could take it as well. This is the Tamedia headquarters, which is our office's first building in Switzerland. And it's also the home of Hermann Blumer, who was the structural engineer for this project. Tamedia is the largest media company in Switzerland, and they've occupied the same riverfront site since the early 20th century. The client had three primary goals for a new 7-story building. The first was to create a workplace that feels like a living room. Next was to make the building feel transparent, both literally and metaphorically as a media company. And last was to maintain a reasonable budget. In response, Shigeru devised a timber post and beam structure wrapped in a glass curtain wall. Switzerland has high energy performance requirements, so sustainability was a key factor here as well. For example, there's an occupiable double facade, which acts as a thermal buffer and also allows for natural ventilation. Here you can see in the image on the right, there's a retractable glass shutter, which is raised to create these pleasant indoor-outdoor balconies. But how do you get to the finished building? On the left, you can see Shigeru's initial concept sketch as compared to the building under construction. They're so similar because Shigeru's work actually begins with the structural concept. The timber structure was precision milled using CNC machines designed by Hermann Blumer, and the robust glulam columns and beams arrived on site like a kit of parts. So remarkably, each column that you can see here, which is 70 feet tall, weighs 2.5 tons each. They were each brought in individually. So you just truck in the column, stand it upright, you're done. That dramatically decreases the construction time. And this is a major advantage, especially when you have an urban site. The glulam columns and beams interlock in these innovative joints, which are secured by an elliptical dowel, so that prevents rotation. There are no metal connections. This form is both functional and elegant. Hermann identified that the structures were too large for the spruce beams alone, and spruce is a softwood. So he concealed a reinforcement plate, which you can see in the diagram on the right. It's the darker shaded portion. And those are made of beech, which is a hardwood. And this is a technique that we often employ to use hardwoods to handle these higher stresses. This is a great example of a design concept that originates with Shigeru's sketch and then is further developed in collaboration with a consulting partner, the structural engineer. Vincente plus N House is a smaller example of a mass timber post and beam structure. This building was designed for a chef and his family with a restaurant on the ground floor and living accommodations above. Like the Tamedia headquarters, the timber columns are continuous from the foundation to the roof, and this is also an urban site, so it was very beneficial that this facilitated quick construction. The joints here are much simpler though, because this is a private project, and so they just require 8 drift pins at each connection. The warm wood structure is complemented by Shigeru's signature paper tube finishes. So in the bottom right, you can see a paper tube screen wall, which also doubles as a wine rack. Next, we'll move on to space frames. So if you ever have the chance to visit Aspen, Colorado, that's the home of our largest project in the US. This is the Aspen Art Museum. It has a woven wood and paper composite facade, which is evocative of the color and the rhythm of the brick buildings that surround it in Aspen. And this porous screen facilitates views into the museum as well as out towards the mountains. Here you can see two views of the Grand Stair, which is an indoor-outdoor interstitial space behind the woven screen. And similar to the experience of skiing, the museum was designed to be circulated from the top down. So you ascend via this Grand Stair and then descend through the galleries. Shigeru believes that the natural context is as beautiful as the art itself, so it's important to highlight the stunning views of nature first. And here you can see the timber space frame, which extends from the rooftop plaza into an indoor cafe. The building is arranged according to the thermos principle, which was developed with a firm called Transolar, who are climate engineers. And in this setup, climate-sensitive galleries are concentrated at the heart of the building and surrounded by less climate-sensitive spaces, such as lobbies, hallways, stairs, and offices. This minimizes the temperature and humidity fluctuations, which is very important for the proper care of fine art. And it also allows the perimeter zones to take advantage of the great views of Aspen. In the left two images, you can again see Shigeru's hallmark paper tube furnishing and finishes, which shows that even a humble material can have a place in a museum. For comparison, on the left, we have Shigeru's initial sketch, and on the right, we have the digital model that was used for fabrication. They're again quite similar. But it isn't as simple as starting with a structural engineer. It was very difficult to figure out the approach for fabricating this. This timber structure went through several iterations, but ultimately cost was a driving factor as well as minimizing material waste. So here you can see some of the initial studies, which included bending and CNC routing. But ultimately, the webs were cut two-dimensionally from custom Baltic birch plywood, which is typically used for furniture. I'm saying custom here. Perhaps you can see in the image on the left, the notation at the top that says strong direction. There are two plies that run in that direction for every one ply that runs in the alternate direction. And this approach had never been done before for building structure. So extensive testing was required to demonstrate the strength of the material. Here you can see a mock-up of the timber structure being built. For the final design, spruce, which is the softwood, is used for the cord, whereas birch plywood was selected for the webs. Birch, a hardwood in this case, was used for these strong connections to reduce member sizes. And as you can see on the left, the web members are joined together with half-lap connections. The plywood came in 12-foot lengths, which was then half-lapped with scarf joints to create these longer members. And in the upper left, you can see how these webs came together in Spearhead's shop. Spearhead is a fabricator that we had used for this project. The timber components were fabricated and shipped to the site in the longest possible transportable lengths in order to minimize on-site construction time. You may notice that this is a little bit odd for a space frame. Usually you see entirely linear members, but here you've got curved members, which may not seem as structurally efficient. However, it created more surface area for wood-to-wood connections, which prevented the use of exposed metal hardware. This structure was developed again in conjunction with Hermann Blumer from Switzerland, as well as Greg Kingsley from KLNA, who introduced me to Edward, and I'm very grateful for that collaborator partnership. You're going to hear again and again these same firm names coming up. And it's not out of favoritism, it's out of this belief in continually advancing a project. And so when you continue to work with the same individuals over and over, you take missed opportunities from past projects and you build on them and you add to them and you grow and advance the discipline itself. So like the Aspen Art Museum, this is Triangle House, which features a space frame for the roof. But this is a much smaller scale and again for a private client. So this building includes an 8-person office with a private residence above. The lower floors have a concrete structure to economically hold the load above, while the space frame roof allows for this large open living space on the top floor. Despite the space frame being nearly a meter deep, there's plenty of daylight here. The space frame was made from European pine, which was selected because it was economical and readily available. At each node, up to 9 timber members intersect, so you can see in the lower right. That's a rather complex joint. And hardwood joints, like what we had at Aspen, were considered here originally, but this wasn't possible due to the particulars of Japanese building code. So here instead, a concealed steel plate was used. It's ultimately a simpler joint. It wasn't the preference in terms of a design and structural resolution, but it demonstrates that regardless of challenging constraints, you can achieve the design vision you seek. You just have to find alternate methods of execution. Now moving on to grid shells. The Centre Pompidou Metz is perhaps one of Shigeru's most iconic buildings and one of the most well-known mass timber structures in the world. This also happens to be the first mass timber building that our office completed. And though it's hard for us to imagine today, the client initially suggested switching to a steel structure, as did the original structural engineers for this project. So in 2003, long before I joined the firm, the Centre Pompidou hosted a competition to design a new museum outside of Paris. The intent was to show more of their 120,000 works, but also to show larger works that wouldn't fit within the 18-foot ceiling of the original Centre Pompidou. Given the architectural significance of the original museum, Shigeru saw this as an opportunity to build an unprecedented structure. The museum was designed as an open pavilion in a park. So unlike its peer institutions, this museum is not a walled-off museum. There aren't large, heavy stone columns. And its 16-foot glass shutters are actually retracted to connect directly to the park. So there's this idea that this isn't a classist division of who belongs in a museum. If you're sitting in the park and you happen to want to pass into the museum and explore a bit, it makes it feel like a much more comfortable environment than if you're not really sure how to approach the building. The building consists of a timber grid shell suspended from a 250-foot tall steel core tower. Despite its sculptural image, it's actually quite simple in plan. It's just a hexagon, which is symbolic of the shape of France itself. 3 gallery tubes below are oriented towards local landmarks. Here you can see the empty interior of one of these gallery tubes. So this one is pointed towards the Metz Cathedral. And the idea is that you can locate yourself within the city while you're in the building. For the iconic roof, Shigeru drew inspiration from 2 seemingly unrelated sources. The first was the cable net roofs of Friado, which have a separate cable structure from the wood enclosure. And the second was the self-supported woven structure of a traditional Chinese hat, which made Shigeru question the necessity of the cable net in the first place. In a typical triangulated grid, you'd have 6 members intersecting at a point, and this yields a very complex and expensive joint. So if you're considering the middle intersection of those triangles, that's 6 individual members coming together. But if you offset that intersection, you can reduce it to just 4 members coming together. So here you can see the influence of the Chinese woven hat. By offsetting the grid, you simplify the method of construction. And that's the ingenuity of Metz. The story of this building's structural resolution is really quite fantastic. So after the initial team of engineers proposed a hybrid structure, followed by a solid wood structure that was twice the roof's budget, the client said to Shigeru, no, you have to change it to steel. But Shigeru wasn't deterred, so he went to Germany to find structural engineers who could take on this challenge. And at the airport, Shigeru was greeted by a Swiss man who he thought was a taxi driver. And he got in this man's car, and he noticed that he had paper tubes in the back seat of his car. And they're talking, and he thought that this was a very brilliant taxi driver, and it turned out to be Hermann Blumer himself. And this was the start of a relationship that has persisted to this day. Every complex timber project, we bring on Hermann Blumer. Shigeru described his conundrum to Hermann, and Hermann immediately reassured him and said within a week he would have a structural solution as well as a cost estimate. So Shigeru felt a lot better, and he went back to Japan. And truthfully, Hermann had no idea. And he actually recounts this in his essay at the beginning of the book, that he wasn't sure how to do it, but he knew there was a solution out there. Independently, Shigeru and Hermann both realized that they not only needed to simplify the grid in 2 dimensions by offsetting from a six-member intersection to 4, but they also had to offset the depth of the members. So rather than intersecting in plane, which would require a complex joint and much more complex fabrication, they actually offset the depth to allow members to bypass one another. So they're stacked. This allowed for just a simple pin to connect these members, and also allowed each beam to act as a Virendale truss. So you can see that the beams themselves have openings and then solid portions. The beams are made of spruce, which is a softwood, and then the joints again are made of beech, a hardwood, to take on the high stresses of the joint. The double curvature of this roof takes advantage of the digital fabrication processes that Hermann Blumer pioneered. And this was the catalyst for all of our subsequent mass timber works. Here you can see a simpler interpretation of the Centre Pompidou Metz structure, which was adapted for a small spa in Japan overlooking a rice field. So this spa grid shell has a woven hexagonal pattern again, and the weave overlaps to allow just simple screw connections. So now we'll take a look at tree columns, which are also a variation of grid shells. I know some of you have seen the evolution of this structural typology in Blumer Lehmann's shop in Switzerland. So at the same time that Shigeru was designing the Centre Pompidou Metz, he was also developing the Nine Bridges Golf Clubhouse, which is a noticeably different grid shell form. The building is essentially a box with a flat roof, but it's supported by these 3-story tall columns. And each column is arranged with a series of 12 radially oriented individual timber members. And you'll notice that the structure bears the same hexagonal and triangular grid pattern as the Centre Pompidou Metz. However, this has a higher density of timber. So it's more slender members spaced closer together. And this allows for a more surface-like reading of the roof structure. So it reads kind of as a continuous form rather than spaced out apertures. The tree columns here are constructed from 3-dimensionally curved German spruce glulam, which takes advantage of the wood grain to take on a structurally efficient form. A more typical low-tech approach would have been to cut these shapes from a large flat sheet, but this method would have been materially wasteful, expensive, and less structurally efficient. Unlike the Centre Pompidou Metz, here all of the members occupy the same plane, so it is taking on those more complex joints. They're notched to accept each other in half-lap joints. And the image in the upper right shows how the roof structure was assembled from prefabricated modules that were just craned into place. 10 years after the completion of the Nine Bridges Golf Clubhouse, the same client commissioned Shigeru to design another project on the site, and they wanted it to be evocative of the original building, but not a copy. So here, Shigeru was tasked to design media and executive training facilities for the golf club. For the main event rooms, Shigeru proposed that they be subterranean because it's very important for a golf course to be quite quiet. So the timber structure on the left, despite being really daylit, that's an entirely basement structure with skylights above. You might notice that this structure is quite a bit heftier than the original Nine Bridges Golf Clubhouse. There are a few reasons for this. First, in the 10 years between the two projects, the Korean building codes changed. So that required more oversizing of the timber structure. And second, instead of having the twisting 3-dimensional curvature, here the wood members only bend in 2 dimensions. So you have an orthogonal grid here. And that allowed it to be built by local builders instead of the builders from Switzerland. And third, Shigeru never wants to repeat a concept in the exact same way. He often likes to create problems for himself if things are just seeming a little too straightforward. So in the diagram on the right, you can see a tree on top. And in the image on the left, you can see a silver basin at the top of each column. Those are actually tree planters. And so the entire roof surface here, in addition to being skylights, has a layer of a reflecting pool. And then these tree planters with integrated drainage down the center of the columns. So adding all of that water and soil on top of the roof structure adds quite a bit of weight to it. Here's a third iteration of the tree column project, even simpler this time. So Yufu Info is a train station overflow room in Japan. And as a public project, there wasn't nearly the budget of a private golf clubhouse. This building has an entirely timber structure, and it was designed to be expressive yet cost effective. So here, once again, we have just an orthogonal grid, but even fewer members than Hazley Hamlet, the previous project. This project was also designed to be fabricated in Japan, meaning that it had to be quite a bit simpler than what was also possible in Switzerland a decade ago. So all of these moves to simplify the structure also meant fewer connections. So these three projects taken together highlight how a similar structural system can be adapted differently depending on budget, code requirements, and access to skilled labor. It also shows how a collaboration with structural engineers and fabricators plays a large role in the actual image of a project and how it evolves over time. Returning to a purer form of grid shell, the last built project that we'll take a look at is the Swatch Omega campus in Biel-Bienne, Switzerland. And at over 500,000 square feet, it's one of the largest mass timber building projects in the world. The campus integrates 3 new mass timber buildings into a historic watchmaking campus. On the left, you can see the Omega factory, which is rectilinear. On the right, the Swatch headquarters, which is more willful. And between the two is Cité du Temps, which is the Swatch Omega Museum. These buildings share a design language which reflects the unified brands of Swatch Omega, but they also express each building's individuality through contrasting structural forms. So we'll take a quick look at the rectilinear buildings, but focus on the grid shell. The Omega factory was built first, and Omega is known as the timekeeper for both NASA and the Olympics. So it was really fitting to have this clean rectilinear form that represents the exacting precision of Swiss fabrication. This building is a post and beam structure with a rigid concrete core flanked by timber watchmaking workshops. Working conditions were a primary factor here. Most notably literal cleanliness. So the Omega factory is the first mass timber building in the world to achieve clean room standards, because it's very important not to get dust in your watches. This certification was important for craftsmanship, but also employee health, because they have a constant stream of ventilation to keep this environment dust-free. So you may not see any air registers in the ceiling. It's because everything just comes through tiny perforations in those ceiling panels. So there's just constant airflow throughout the day. It can create a dry environment if it isn't managed properly. Also, one thing you might hear about mass timber structures that's a concern if someone is building a lab building, for example, is that mass timber vibrates. It's a very flexible material. That makes it a safe material that can be resilient in many ways. But this is not desirable if you're creating intricate small watches. And so to counter this, a concrete topping slab was actually added to the CLT structure to keep it from vibrating, which is necessary for making the watches. So in contrast to the maturity of the Omega building, Swatch is a much more playful, innovative, and provocative brand. And though the serpentine form that you can see here appears rather unrestrained, the facade and the structure are each responsive to practical design constraints ranging from code and zoning to material properties and building services. So here, the sculptural grid shell covers 4 office floors connected via 3 concrete cores. The timber structure is composed of a 7-foot grid of interlocking timber beams that seamlessly transition from the wall to the roof structure. The office space below is open and flexible, fostering collaboration. So the idea here is the entire company under one roof. There's no private office of an executive who's off limits. Anyone can be open for collaboration. The Swatch headquarters was designed in a truly contemporary manner without traditional construction documents. Instead, a parametric model accounted for the specification of 7,700 timber members with a precision of 0.1 millimeters. And this allowed the wood to fit together perfectly on site like a puzzle. In a more typical building project, you might see errors impacting up to 15% of the parts delivered to the site. But because of this approach with the parametric model, this complex grid shell had only a 0.11% error rate, meaning only 72 of the 62,792 prefabricated roof elements that came to site had an error. This is a testament to the interdisciplinary and collaborative nature of this design project. SBA worked extensively with Hermann Blumer of Creation Holtz, as well as digital facilitators Design to Production, who created the digital fabrication model and resolved all of the conflicts that would have occurred from integrating building services into this project. And this dynamic team has worked together for nearly 2 decades, beginning with the Centre Pompidou Metz. A fun side story to that is that we didn't actually know that this entire consulting team had worked together on Centre Pompidou Metz. The digital facilitators were contracted directly by the builder in that prior project. And as we learned who's had a hand in creating these projects, we began bringing them in earlier and earlier in our projects to use their expertise from the outset. So here you can see the building envelope, which integrates structure, building services, and the facade. Since the maximum footprint of the building was fixed due to site constraints, an unnecessarily thick facade envelope would have reduced the building's usable floor area, and this wasn't viable for the client. So to resolve this, Shigeru drew inspiration from the original Swatch watch. And the reason that Swatch watches had become famous was that they integrate components directly into the plastic case of the watch itself, which reduced both the cost and the thickness of the watch. So Shigeru's approach here was similar. Instead of layering discrete, separate layers of structure and then building services and facade on the outside, he allowed them to pass through one another. The facade nests into the structure and the building services pass through the timber structure. This is quite a bit more complicated to coordinate, and hence why we worked with Design to Production. So prefabricated openings were tailor-made to the size of electrical cables, sprinkler pipes, and cooling pipes, with cutouts staggered and mindful of the wood grain so that the structure would not be weakened. The roof is a 120,000 square foot surface with 2,800 apertures arranged in a very spirited pattern. It might seem randomized, but each has a particular reason. So first we have the ETFE cushions, which are white and pillow-like. If you're not familiar with that material, it's kind of like a fabric sheet. So you can see through it, it's translucent, it glows in the daylight. And if you're looking at it from the exterior, it'll glow at night when the lights of the building are on. This is a great material for diffuse daylighting, which helps to create a glare-free environment for offices. Next, we have CLT panels at the high points of the roof to reduce solar heat gain, and PV panels on the top and the south side to offset the building's energy consumption. The Swiss cross form that you can see towards the middle of that image actually acts as both structural bracing and acoustical absorption. And at the lower level, that's the only place where there are glazed panels because there are views out to a neighboring park. The Swatch grid shell reaches over the street and sits atop Cité du Temps, which is the third building on the site. This museum and conference center acts as the interface between the Swatch and Omega brands. And an interesting issue to consider here is the differential movement of each of these buildings. This museum incorporates the architectural language of its neighbors with playful concrete arches at its base and a rectilinear timber structure above. The mansard roof is evocative of the campus's historic buildings. The Omega factory has a concrete core and topping slab, but Cité du Temps is an entirely timber structure above the ground floor. So it has glulam columns and beams, and CLT floor slabs and core panels. This is an outwardly simple building, but the interfaces require great attention to detail. So as you saw on the previous slide, the Swatch grid shell sits right on top of this building, and on the opposite side, it actually connects to these historic buildings on the campus. So despite being such an enormous project, the buildings were constructed from 160,000 cubic feet of certified Swiss timber. It's kind of a difficult number to wrap your head around, but considering the growth rate of Swiss forests, it would only take 10 hours to regrow this quantity of wood domestically. So that's 0.1% of Switzerland's annual timber production to create what we think is the largest timber building project in the world. So to conclude, we'll take a look at just one project that our New York office is currently working on, which is the Kentucky Owl Park. This is a 500,000 square foot bourbon distillery in Bardstown, Kentucky, sited on a 420-acre reclaimed limestone quarry. This distillery sits on a peninsula at the center of the site and is surrounded by production buildings, including a bottling center, a craft cooperage, which is where the barrels are made, rick houses where the bourbon is aged, as well as a visitor center and a train station. For the visitor center, we drew inspiration from the structure of a bourbon barrel itself. So the dendriform columns are a combination of timber and steel, evocative of the wood staves and the steel hoops that make up a bourbon barrel. Here you can see the 3 pyramids of the distillery. The adjacent lake water is used to make the bourbon itself. So in the first pyramid, visitors gather for tours and are educated about the bourbon making process. In the second pyramid, you can see the interior on the right. This is where distillation itself takes place. And the shape of the pyramid actually comes from Shigeru's pragmatic idea to efficiently house this 60-foot tall column still at the center of the building without creating a large rectilinear mass in the center of this site. So this minimizes the overall volume of the building. And then in the last pyramid, the bourbon is bottled in preparation for aging. The roof structure here might seem quite familiar. It's an evolution of the Aspen Art Museum's wooden space frame. So here again, with each project, we're building on past studies, but the complexity here comes from the angle of the space frame and how the 4 faces of the pyramids meet and come to those joints at the intersections. To do this, we once again teamed up with the structural engineers from Creation Holtz and KLNA, as well as design facilitators Design to Production and fabricators Spearhead. This is a sheet from our schematic design set. We call this a reference geometry drawing. So in the diagram at the left, green represents the outer face of glass, blue is the top face of the upper chords, and red is the bottom face of the lower chords. So in actuality, we're studying 3 nested pyramids geometrically. And we document this geometry through trigonometry rather than rounded numbers. So we keep a parametric approach as long as possible because changes are bound to happen and the complexity only increases over time. So our clean 90-foot dimension applies to the outer face of structure, which aligns over the foundation. And then we begin to consider facade module sizing. Not sure if you can read all of that down there. It's quite crazy to have that as your dimension string. So this is schematic design. We don't know who our facade manufacturer is yet. This needs to stay in this format until we know every last detail and we can get down to a reasonable measurable size of tolerance. In parallel, we're working with our fabricators Spearhead to optimize our material sheet layouts. So thinking about the structural form, the size that the material comes in, and how we should change our form so that we don't have too much material waste. And then we're considering maximal transportable lengths. So literally, what trucks can we get to the site? This gets down to turning radii driving into Kentucky. And in addition to member sizing, our structural engineers also contribute to the assembly sequencing, including site staging and maintaining the structural integrity of each face as it's lifted into place. So this is, again, all only at the schematic design level. So we'll conclude with an animation of the project. So I'm looking forward to being actually able to add Kentucky Owl to this grid of completed projects. Just in conclusion, I think we can learn so much more by discussing the trajectory of a project rather than focusing on the beautiful final image that we see in books, on the internet, etc. And prior to the publication of Timber and Architecture, Shigeru Ban was the only one who knew the entire content in that book, in this presentation, etc. Shigeru teaches in architecture schools every semester throughout the year, has for 35 years. And so it's really important to him and all of us at SBA to disseminate that knowledge, to share it, to try and grow the collective field of timber in architecture. So just a few key takeaways here. Across the spectrum, from simple plywood houses to complex grid shells, wood has a diverse range of possibilities that you can pursue. And selecting the appropriate material and application is a critical factor in our effort to build responsibly and reduce carbon emissions. This doesn't mean wood is always the answer, or that more wood is inherently a better approach. And lastly, this is a highly collaborative field. It's always important to engage these key consultants early in the process, continue to champion their role. A lot of times we as architects are defending the need to the client to have a structural engineer and a fabricator right at the early phase of the project. But this immensely benefits the final result and saves the client quite a bit of money. And lastly, even the book was a collaboration. Everything we do is a collaboration, and the best way that we can advance this work is to continue to work together on it. Thank you.